Hello, I'm Sean, number 10.
Hello, I am Isaran, number 19.
Today we are going to present about BTS physics project. Table of content 1.1 Data and graphs. Distance time graph, velocity time graph, acceleration time graph, and result table. 1.2 Explanation of data and graphs. 1.3 Free body force diagram. 1.4 Newton's law. 1.5 Kinetic energy. 1.6 Gravitational potential energy. 1.7 Energy transfer. 1.8 Work done and power. 1.9 Momentum, and 1.10 Discussion. 1.1 This is the data and graphs we've collected. You can see all of them together in this slide. In the next slide, we will explain each graph individually.
This is the distance time graph. In 0 seconds, the distance is still also 0 because the train hasn't moved yet. Then during up to 40 seconds, the train considerably moves from around 15 to 468 meters. And between 45 to 55 seconds, every 5 seconds add up to around 25 seconds every time. Subsequently, during 60 to 85 seconds, the train stops for 20 seconds at St. Louis station. That's the distance remained at race, which is around 581 meters. Next, the train steadily grows from around 588 to 1,155 meters between 90 to 165 seconds. And finally, the train arrived at Chongqing Station and stopped, which ends its destination at 1,161 meters.
1.2 Velocity and time graphs. Between 0 to 10 seconds, the train gradually increases its velocity from 0 to 3.5 meters per second. Then, between 15 to 20 seconds, the train velocity dramatically increases and reaches its peak at 24 meters per second in 25 seconds. After the train reaches its peak, it's considerably dropped to 3.12 meters per second in 60 seconds. This is because it's going to reach St. Louis Station, which is why it slows down. Afterwards, the train velocity is 0 meters per second between 65 to 85 seconds because it stopped. Then the train starts to move forward at the velocity of 1.35 to 2.4 meters per second between 90 to 95 seconds. At that time, the train starts to gain back its lost velocity and steadily increases its velocity to 11.126 meters per second in 110 seconds. Next, the train maintains its velocity of around 9 to 10 meters per second. Then it moderately plunges its velocity to 1.59 meters per second in 170 seconds. Lastly, it stops at Changnan Station, which makes its velocity rest by 0 meters per second.
Next is the acceleration time graph. Between 0 to 10 seconds, the train accelerated from rest to around 0.6 meters per second squared and has a jerk which made it decelerate down to 0.1 meter per second squared in 10 seconds. Next, the train rapidly rises from 0.95 to around 2 meters per second squared during 15 to 25 seconds. And afterwards, during 30 to 60 seconds, the train sharply decelerates to negative 1.5 578 meters per second square and considerably fluctuates between around 0.1 meter per second square and 0.4 meter per second square. When the train arrived at the station, it jerked, which made it decelerate at around negative 0.6 and 65 seconds. The train is at rest between 70 to 85 seconds because it is stopped at the station. At that point, between 90 to 100 seconds, the train increased quickly to 1.6 meter per second square. Then between 105 to 150 seconds, the train decelerated and accelerated up again because it needs more power for it to turn around the corner. After 155 to 170 seconds, the train declined from around negative 0.2 to negative 0.3 meter per second square. To end the train jerked it, thus it decelerated at negative 0.3 meter per second square and stopped it in 135 seconds. This is the free body force diagram that we made. In the upper left diagram, it is when the train is stationary at Surasat BTS station. The contact force on Earth from the train is pushing it down, and the contact force from the train from the Earth on the train from the Earth is pushing it up. And the gravitational force on the train from the Earth is pushing the train down. But the gravitational force on Earth from the train, which is the reaction force, is pushing it up. So it is zero to it is not moving. Then the left diagram under the stationary picture is when 5 seconds after it has left Surasat BTS station. The gravitational force on the train from the Earth is pushing it down. The gravitational force on Earth from the train is pushing it up. And the contact force on the Earth from the train is pushing it down. And the contact force on the train from the Earth is pushing it up. And because it is moving, there are traction force and friction force that is pushing it under each other, and the drag and thrust force that is pushing it under. And on the right is when the train is on the bend, which there are friction force in the wheels and centripetal force which follow the path. And for the 5 seconds before the train enters Shanghaisi BTS station, it's the same as the 5 seconds after it has left Surasat BTS station.
1.4 Newton's law. Number 1. When it is stationary at Sirasak BTS. When the train is at rest in Sirasak station, the Newton's first law, also known as the law of inertia, is applied. Under the equilibrium condition, an object that is at rest will stay at rest unless the force acts upon it. So the train is still at rest because the force acting on it is zero. Question 2. 5 seconds after it has left Surasak BTS station. After 5 seconds, when the train left Surasak station, Newton's second law, or the law of force and acceleration. The acceleration of an object is directly proportional to the net force exerted and inversely proportional to the object's mass. And the third law, or the law of action and reaction. For every action, there is an equal and opposite reaction is applied. This indicates that the force acting on the moving train is the product of the mass and acceleration. And when the train is accelerating by traction and thrust force, the friction force is acting at the same time. Number 3. 5 seconds before the train enters Shanghaisi BTS stations. 5 seconds before the train enters Songnonsi station, the train needs to slow down before hitting the brake. Newton's first law, or the law of inertia, is applied. This indicates that the train uses friction force and air resistance to stop.
Number 4. Why do passengers fly back or feel a force pushing back when the train begins to move? The answer is passengers fly back or feel a force pushing them back when the train begins to move because the train is accelerating. The passengers are not accelerating, which is the law of inertia, until the force is acting on the passenger. The friction between the floor and the passenger B creates a net force. So when the trains are accelerating, the passengers continue to travel for a small amount of velocity. This causes the train to move forward when the rest of the body is not moving, which makes the passengers fly back and feel a force pushing them back. In other words, to maintain their velocity, passenger must experience the same force that is accelerating the train. 5. Why does this not happen when a passenger holds onto the strap hanger or anything on the bus? Passenger do not fly backward or feel a force pushing back. If they lean back on the BTS or hold onto the strap hangers or handrails because they will have support for their balance. They will accelerate same time as the train, and the force that happens that spreads and transfers to the strap hangers or handrails of the bus.
1.5 Kinetic energy. The kinetic energy of the BTS can be calculated using the formula half mv squared, m meaning mass and v meaning velocity. For this example, we will calculate the kinetic energy 3 times. First, when the train starts at 5 seconds, second, when the fastest point, and third, when the train is nearing Cheongnon-si at 160 seconds. From our research, the mass of the BTS is about 138 tons or 138,000 kilograms. For the calculation, we use the value from the table we got and implemented into the equation, such as the first one. Half times 138,000 and times by the velocity from the table we got, which is 3.058 squared, getting the answer of 0.645 megajoules. And the answer for the second one is 39.691 megajoules, and for the third one is 0.822 megajoules. 1.6 Gravitational potential energy. Gravitational potential energy, aka GPE, can be calculated using the formula gravitational potential energy equals mgh, m meaning mass, g meaning gravitational field strength, and h meaning height. The height of the BTS is 12 meters. We got it from the official website. The reference is down below if you want more information. The gravitational field strength of Earth is 9.8, but we round it up to 10 for easier calculations. In the calculations, we calculated the GPE equals the mass, which is 180,000 times 10, and then which is the gravitational field strength, and then times 12, which equals 1,800,000 times 12, and the final answer is 21.6 megajoules.
Energy transfer 1.7. Energy used to move the train forward. The train uses kinetic energy, which is harnessed by transforming it to electrical energy by using 750 DC voltage to make rail traction power and convert the electrical energy by using traction conversion units. Energy losses. The train lost its thermal, theoretical, potential, and kinetic energy as in energy transfer along the train's journey. The trains also transfer thermal, theoretical, potential, and kinetic energy to the air and grid as it moves.
1.8 Work done and power. Work done can be calculated using the formula work done equals force times distance. We can calculate the force of the train by using the formula F equals ma, or force time equals mass time acceleration. Power can be calculated using the formula P equals work done divided by time. We will calculate work done and power three points. First, when the train just started at 5 seconds, and second, the fastest point, which is a 25-second point, and third, at the end point, which is 175 seconds. In the calculation, the force is calculated using the mass and distance, which is 180,000, and 0.612 for the acceleration. And work done is done by taking the force, which is, for the first one, it's 110,160 newtons, times by the distance, which is 15.29 at 5 seconds, which equals to 1,684,346.4 joules. Change that into a bigger unit would be 1.68 megajoules. The power is calculated by taking the work done, which is 1,600,000, as I've said before, divided by 5, which equals to 0.337 megawatt. And for the second one, it is 93.19 megajoules, and for power it is 3.73 megawatt. For the third one, it is work done is 66.46 megajoules, and for the power it is 0.37975 megawatts. 1.9 Momentum. Momentum can be calculated using the formula P equals mv. M stands for mass and v stands for velocity. We will calculate 3 momentums at 3 different points. 1. When the train just started. 2. The fastest point, and 3. Nearing its end. Momentum is proportional to velocity, meaning as velocity increases or decreases, momentum also increases or decreases. For the example 1, we did P equals 180,000 times 3.058, which is mass times by the velocity, which equals to 550,440 kilograms meters per second. The same for the second one, which equals to 4,317,120 kilograms meters per second. And for the third one, it is 621,360 kilograms meters per second.
1.10 discussion. Our method is feasible for backup as we travel from to a station to Chauncey station. We start opposite of the building and we measure our delta miles by looking at the opposite building of us. Proceeding Google Maps. Accuracy. Google Maps could be result may discourage due to factors like change in surrounding, changing time for stopping to drop off passenger and wait for new passenger, or changing railway tracks. Camera angle could be inaccurate, which could lead to accuracy when plotting and measuring. Mass of the objects will change if there are more people there. Different driver may lead to different train speed, and if repeat the X-ray many times at different times, record from different angles and surroundings, get better equipment like a camera, stabilizer, etc., and contact BTS station company to get more accurate information and insights.
Here are the pictures and videos. Thank you.